Question number 9. Which statement about intermolecular force is not correct? Intermolecular force exists between all simple molecules. Yes, even if it's just simple van der Waals forces, then they exist. So A is correct. Hydrogen bonding occurs between HBr molecules. No, you only get hydrogen bonding when you get a hydrogen to an oxygen, a hydrogen to a nitrogen, a hydrogen to a fluorine, and you get a large difference in electronegativities, so you get a large polarity, a large delta plus and delta minus, a large polar bond, and then the intermolecular bonds are strong between those large polar bonds in each of the different molecules. So B is incorrect. Let's just check though. Hydrogen bonding is the strongest intermolecular force in liquid ethanol. Yes, hydrogen bonding is always the strongest intermolecular force, and ethanol does have an oxygen bonded to a hydrogen. Hydrogen bonding occurs between CO and HN in proteins. Yes, that's true, because you've got a hydrogen bonded to a nitrogen. Anywhere where you've got a hydrogen bonded to a nitrogen, a hydrogen bonded to an oxygen, a hydrogen bonded to fluorine, you've got hydrogen bonding. So the answer is B. For the next one here, I've got a reaction here, and I'll just do spoilers on this one so you can see what's happening. We've got the enthalpy of formation. So we're forming C2H6, we're forming 6F2, we're forming C2F6, and we're forming 6HF. When you form things from their elements in their standard states. That's how you normally find them in the laboratory. Carbon is a solid, fluorine is a gas, and hydrogen is a gas. So they're being formed from these things here. And when I form the C2H6 here, it says it's minus 84. So I'm forming it from the elements in their standard states, and I'm making this minus 84. Fluorine is already in its standard state, F2, that's as you normally find it, just a normal element. It's not combined with any other atom, so I've not actually had to make it at all. So the enthalpy is 0 for that. To make C2F6, then it's minus 1334 here. And to make 6 lots of HF, I don't know. That's what I need to find out for HF. Now then, they're coming from here, and they're coming round to here. So they're coming from here, across to here. That's the same as going from here round to here. So now then, what I've got to do is I've got to take any signs that are the wrong way round and reverse them. So minus 84 is the wrong way round. We've got elements in the standard states making that, forming it. It's got to come round to here now, because it's got to go from there to there, which is the same as coming round from here to here. A process known as Hess's law, in that if it starts in the same place and ends in the same place, it doesn't actually matter about the route of the reaction. So minus 84 becomes plus 84, 0 becomes 0. This is going in the right direction, minus 1344, and this is going in the right direction, and we don't know what that is, so I've called that a question mark. So, and there overall it equals minus 2898. So 84, add 0, take away 133, add question mark, equals minus 2898. Okay, so I'm going to take the question mark and I'm going to leave it on that side, and I'm going to take all of these and reverse the signs. So minus 288 plus 1344 when I take it across the equal sign, minus 84 when I take it across the equal sign, equals minus 1638. That's the question mark. But that's for 6 lots of HF, 6 moles of HF, and it wants to know what's the enthalpy of formation for HF. That's the enthalpy, the amount of heat energy when 1 mole is produced. So if I make 6 moles, it's 1638, but for 1 mole I need to divide by 6 is minus 273, so my answer is B.